Good evening, biochemist. I hope everyone is having a great day on this fourth day of quarantine. So let's keep this train rolling on lipids. And for this lecture, we're going to talk about lipoproteins. So lipoproteins are a biochemical assembly of both lipids and proteins. So the purpose of these lipoproteins are to enable nonpolar lipids to move within the water-based solution of the bloodstream. So we're talking about sequestered cholesterol esters and triglycerides here. So over here on the right is what a typical lipoprotein particle looks like. You're going to have a single layer outer shell of phospholipids and cholesterol, and you're going to have these embedded proteins that we call apolipoproteins. So the purpose of the apolipoproteins are twofold. So one, they provide stability. So a lot like cholesterol does with a cell membrane, the apolipoproteins help stabilize this lipoprotein particle and keep it from being too fluid. It also determines the functional identity and the destination of each individual type of lipoprotein particle. Okay, so in the last slide, I mentioned that lipoprotein particles are used to sequester cholesterol esters and triglycerides, but we haven't really talked about what those are yet. So a cholesterol ester is just like any other ester that we've talked about so far this semester. It's formed from a fatty acid, which acts as our carboxylic acid residue, and the cholesterol, which acts as our alcohol residue. Okay, so what is the purpose of a cholesterol ester? So remember when we first talked about cholesterol, I told you that they're amphipathic molecules. So the bulk of a cholesterol molecule is hydrophobic, and you have that single hydroxy group that's going to be hydrophilic. So that amphipathic structure leads to some unique issues when you try to transport cholesterol. So it's too hydrophobic to just move by itself through the bloodstream, but it's too hydrophilic to just pack into the core of a lipoprotein particle. So by making it into an ester, we're going to make it more hydrophobic. That way we can pack it into the middle of these lipoprotein particles. Okay, so back to lipoproteins. So we're going to divide lipoproteins into 5 classes based on their density compared to the surrounding plasma membrane. So our most dense, as you might imagine, are high density lipoproteins. And now I want you to look at these 3 columns that I have arrows pointing to. You'll see that high density lipoproteins, or HDL, are the smallest in diameter, have the least amount of triglycerides, but have the highest protein content. And this is a trend we're going to see as we move down this list. So our next most dense are low density lipoproteins. They're going to be slightly bigger than HDL. They're going to have a little bit less protein and a little bit more triglycerides. Our next most dense class are intermediate density lipoproteins, or IDL, followed by very low density lipoproteins, or VLDL. And then the largest are chylomicrons, also known as ultra low density lipoproteins. Now notice how much bigger these chylomicrons are than HDL. So your average chylomicron is going to be over 100 times as big as an HDL. And this is because they are just stocked full of triglycerides. So over 80% of the mass of chylomicrons come from triglycerides. Very little of it is protein content. Okay, so what do these lipoprotein particles do? Well, we're going to divide their functions into 3 separate pathways: the exogenous pathway, the endogenous pathway, and the reverse pathway. And just like in the last lecture, that graphic that I put up with all the steroid hormones, you don't need to memorize this pathway graphic. You just need to be able to understand it and answer some questions about it. So let's start with the exogenous pathway, which describes what happens to dietary fat that we ingest. So starting with our dietary fat, it's going to be absorbed by enterocytes of the intestines. In the intestines, they're going to join with ApoB48, which is one of the apolipoproteins that we talked about earlier, and that's going to form a nascent chylomicron. So this nascent chylomicron is then secreted to the lymphatic system and then to the bloodstream via the activity of ApoB48. So we talked about the purpose of the apolipoproteins are to add some rigidity, add some structure to the lipoprotein particles. Well, they also determine where the lipoprotein particle goes. And this specific lipoprotein particle leads the chylomicron into the bloodstream. Once we're into the bloodstream, this chylomicron is going to bump into a high density lipoprotein, and that HDL is going to transfer over to other apolipoproteins, ApoE and ApoC2. So once that happens, we now have a mature chylomicron with 3 different apolipoproteins. And one of those proteins, ApoC2, is going to activate another protein called lipoprotein lipase. So this is an enzyme that is going to hydrolyze triglycerides into free fatty acids. These free fatty acids are then going to be able to be absorbed by adipose and muscle tissue. So once enough of these triglycerides have been cleaved, have been broken down into free fatty acids, our mature chylomicron is going to get smaller and smaller. And this is going to cause protein ApoC2 to dissociate, and it's going to give it back to a high density lipoprotein. So now we have what we call a chylomicron remnant. And this chylomicron remnant is led to the liver for breakdown through the action of protein ApoE. Okay, so what kind of questions could I ask you on the exam about the exogenous pathway? So one example is to label the lipoprotein particles as nascent, mature, or remnant. Okay, so nascent means new or young or beginning to exist. So this is going to be a particle that is not quite mature yet. Something has to happen for it to become mature. So in the case of a chylomicron, it needs ApoE and ApoC2 before it becomes mature. So a remnant is a remaining or a fragment, something that's left over. So when we're talking about lipoprotein particles, a remnant is going to be what's left of a mature particle when it can no longer perform its function. So in this case right here, once chylomicrons give away the ApoC2 protein, they are no longer active and they would be considered remnants at that point. Okay, so let's look at the next question. So what is the function of protein ApoE? So ApoE is what is going to guide the chylomicron remnant back to the liver. So that's all you would have to tell me for the function of ApoE. It's guiding the chylomicron remnant back to the liver for breakdown. And if I asked you what is the primary lipoprotein particle involved in the exogenous pathway, you would tell me chylomicron or ultra low density lipoprotein. Okay, so let's take a look at the endogenous pathway on the left here. So endogenous means within, so this is going to be the pathway for lipoproteins created by your body. So you're going to have triglycerides and cholesterol are both going to be synthesized in hepatocytes of the liver. They're going to join with ApoB100, which performs a similar function to ApoB48. It's going to trigger the secretion process and get this lipoprotein particle into the bloodstream. So same thing, HDL is going to transfer over ApoE and ApoC2 to create a mature, very low density lipoprotein. So just like before, lipoprotein lipase is going to be activated by ApoC2. It's going to hydrolyze triglycerides into free fatty acids that can be absorbed by our adipose and muscle tissues. And then once enough of these triglycerides have been broken down, the VLDL is going to lose ApoC2, giving it back to HDL. So at this point, it is a remnant. So a very low density lipoprotein remnant is known as an intermediate density lipoprotein. So these IDLs can go down 2 separate routes from this point. So about half of them are absorbed directly by the liver for breakdown. And this is due to the action of protein ApoE. The other half get hydrolyzed further, this time by a different enzyme called hepatic lipase. So just like LPL did before, hepatic lipase is going to hydrolyze triglycerides into free fatty acids that can be absorbed by skeletal muscle and by adipose tissue. So once this happens enough and the triglyceride content gets low enough, ApoE is then going to dissociate. So ApoE is going to go back to an HDL. So at this point, we have a new remnant, and this remnant is going to be an LDL, so a low density lipoprotein. And there are three different fates for an LDL. So first of all, LDLs can be absorbed by most cells directly due to the action of protein ApoB100. They can also be broken down by macrophages and deposited as plaques in our arteries, or they can be led to the liver for breakdown due to the action of protein ApoB100. So let's take a look at the reverse pathway. So this is the simplest of the three. This one only focuses on HDL. So you have HDL synthesized by the liver by joining phospholipids and ApoA1. So this ApoA1 causes a secretion of the HDL to the bloodstream, and there it travels around and picks up free cholesterol from other cells and returns it to the liver for breakdown. So what kind of questions could I ask you about these pathways? One thing I could do is just ask some simple labeling questions. So if I got rid of the names of all the lipoprotein particles here, could you label them? Could you identify which one is a VLDL and when that becomes an IDL and finally an LDL? I could also ask you about function. So I could ask which lipoprotein particle is responsible for scavenging cholesterol from other cells and bringing it back to the liver for breakdown. And you would tell me HDL is responsible for that via the reverse pathway. Okay, so remember from the last slide, we said one of the possible fates of a low-density lipoprotein particle is that it can be broken down by macrophages and deposited as plaque in your arteries. This is a disease known as atherosclerosis, and this is where your arteries narrow due to the buildup of this plaque. And so we can tell if you're at risk for this by measuring your serum concentrations of cholesterol and triglycerides. So what are the healthy levels? Well, you want your cholesterol concentration from HDL to be greater than 40 milligrams per deciliter. You want the cholesterol from LDL to be less than 100 milligrams per deciliter. You want your total cholesterol concentration to be less than 200 milligrams per deciliter. And you want the ratio of cholesterol from LDL and cholesterol from HDL to be less than 2.5. So some of you in here, especially those of you who are closer to my age, might have had a lipid panel done before. So these typically measure three quantities. So they're going to measure the total cholesterol concentration, the cholesterol concentration from HDL, and your triglyceride concentration in your blood serum. And so from this, you can calculate the concentration of cholesterol from LDL using this first formula, and you can calculate the concentration of cholesterol from VLDL using this second formula. So before we wrap up today, I want you guys to answer a question for me. I want you to tell me if I am healthy. So what I want you to do is look at the 4 requirements for healthy levels and the 2 equations on the previous slide. I want you to pause the video, perform the calculations, and then figure out if I'm healthy or not. Okay, so let's work through this and see what the results are. Okay, so the first thing we want is for our HDL levels to be greater than 40 milligrams per deciliter. So it looks like we are good there. Okay, so the next thing we want is LDL levels to be less than 100. So we have to do a calculation for this one. So our cholesterol concentration from LDL is going to be equal to our total cholesterol concentration, which was 182 milligrams per deciliter, minus our HDL concentration, which is 51, minus triglyceride concentration, divided by 5. So pulling out my calculator, I get 119.4. So that means I am not healthy. Okay, but for completeness, let's go ahead and calculate the other 2 values. Okay, so total needs to be less than 200. We're given a total of 182, so we're good there. And our ratio needs to be less than 2.5. So for our ratio, we have 119.4 milligrams per deciliter divided by 51 milligrams per deciliter. Pull out our calculator and let's see what we get. And it looks like we get 2.2 3, 4. So we're good there too. Just got to lower my LDL levels a little bit.